Let's do some problems now on field theory so that we understand all the theory that we've developed in the previous videos. So let me start with some simpler problems. So let F be any field. Show that F contains Q or Z mod Pz for some P. Okay, so this is actually not really a problem. I just wanted to start with this because it captures the main starting point for field theory for some prime P, I should say, prime integer P. Let F be a field, show that it contains either Q or Z mod Pz. So this solution is very easy. As I said, we have multiple times discussed this. So consider the unique ring homomorphism from Q or rather Z to F. For every ring, commutative ring with unity, there is a unique map from the ring of integers to it. So consider the unique ring homomorphism from Z to F. We know that by the argument that a subring of an integral domain is an integral domain and the first isomorphism theorem, we know that kernel phi is a prime ideal of Z. This came up in when we discussed finite fields also. It's a prime ideal of Z. So there are two cases. If kernel phi is 0, then phi is injective. What are the prime ideals of Z? These are ideals, either the 0 ideal or generated by a prime number. So if it is 0 ideal, it's injective. That means Z is contained in F. By abuse of notation, I can think of Z actually as a subring of F, because Z has an isomorphic copy of itself in F. By treating that isomorphic copy as Z, I can think of Z as F. But how can you get Q then? But because F is a field, every integer, positive integer, or every non-negative integer n, rather every non-zero integer n, has an inverse in F. So Q itself is contained in F, right? Because 1 by n is there for all non-zero n. Once 1 by n is there, m by n is there. Okay, so every rational number will be there, so Q itself is contained in F. So that's one case. If kernel phi is non-zero, this means kernel phi is equal to Pz for some prime number. In this case, Z mod Pz is contained in F. By the first isomorphism theorem, Z mod kernel is isomorphic to its image, which I am thinking of Z mod Pz. So Z mod Pz is contained in F. So F contains Q in case 1 and F contains Z mod Pz in case 2. So that finishes the solution. In other words, what we want to remember is, hence, every field that you can work with is an extension field of Q or Fp for some P. And remember, it has to be exactly one of them, as this solution shows. If it contains Q, it cannot contain Fp. If it contains Fp, it cannot contain Fq for some other prime Q. Okay, so it is exactly one. So basically the world of fields sits above either Q or F2 or F3, F5, F7 and so on. So you have fields here, you have fields above this, you have fields above this and above this and so on. So every field is above either Q or F2 or F3 and it's unique. So there is no connection between this. These are all disconnected. In this case, we say characteristic is 0. In this case, we say characteristic is 2. In this case, we say characteristic is 3. In this case, we say characteristic is 5. In this case, we say characteristic is 7 and so on. Right? So characteristic 0 fields are all living above Q. Characteristic 2 fields are all living above F2 and so on. So these bottom things are called prime fields. So prime fields are those that are at the base of every field. So it's either Q. So prime field of a characteristic 0 field is Q. Prime field of a characteristic 2 field is F2. Prime field of a characteristic 11 field is F11, and so on. So every field is an extension of these. So that is the first exercise. So you have every field is like this. So second exercise, let K be a field and let F be its prime field. Remember, there is a uniquely determined prime field. Let K and L be two fields, I should say, and let F be their prime field. So what we have is K is here, L is here, and they are both over F. So F is in fact, so F is Q or ZF FP for some P. Right, so F is Q or FP. So I want to do an exercise which is not dependent on which case we are dealing with. So F is an arbitrary prime field, it's either one of those, and K and L are two fields. Then show that, so this came up when we talked about field homomorphisms. So show that any field homomorphism sigma from K to L is an F homomorphism. Right? So in other words, that is, any field homomorphism fixes, any field homomorphism sigma from K to L satisfies sigma of A is equal to A for all A in F. That means it fixes every element of F. This is not true, remember, if you take an arbitrary field extension. If F is arbitrary and K and L are two arbitrary field extensions of F, not every homomorphism is necessarily an F homomorphism. This is only a statement for prime fields. Okay, so I will quickly do this. This is not difficult, and I will start the solution and leave the actual solution to you, the detailed solution to you. So the point is, we must have sigma 1 is 1. So this is okay. This is forced for us because sigma is a ring homomorphism. Any ring homomorphism sends 1 to 1. And a field homomorphism is actually just a ring homomorphism. So once sigma 1 is 1, so sigma n is n. So I'm going to first consider the case F equal to Q. Sigma n is equal to n for all n in Z, because sigma 2 is sigma 1 plus sigma 1, which is 2. And once sigma n is n, sigma, right, sigma m by n is equal to sigma m by sigma n for all m by n in Q. See, this is because the first condition is clear. For the second condition, what we have is n times m by n is m, right? So this implies sigma n times m by n is equal to sigma m, which is m. We have already showed that sigma of integers are those integers itself. Sigma fixes integers. This is clear because sigma 1 is 1. But this means sigma is a field homomorphism. So this means sigma of n times sigma of m by n is equal to m. Okay. So actually what I should really write is m by n. So sigma of m is m, sigma of n is n. So sigma of n times sigma of n by n is m. Sigma of m by n is equal to m by sigma of n, which is, so I'm assuming of course n is non-zero here, which is m by n. Okay, so sigma fixes every rational number. So sigma is a Q homomorphism. The argument is even easier for Fp, because Fp is actually nothing but 0 bar, 1 bar, 2 bar, up to p minus 1 bar, right? So sigma of 1 bar is 1 because one multiplicative identity goes to itself. So sigma of a bar is a bar for all a bar because each of them is 1 added to itself that many times. So this finishes the solution, right? So any homomorphism of extensions is in field extensions is in fact a homomorphism over the prime field. Here very important point is that f has to be q or z mod pz, otherwise it's not true. Okay, so that's a nice thing to know. You don't need to separately check that it fixes q or it fixes fp point wise. Okay, so the third exercise, which is also very simple. So let k over f be a field extension of degree p where p is a prime integer. Then there are no intermediate fields. What I mean is, that is, if f is contained in L is contained in K, then L is equal to f or L equal to K. So what I really mean is that there are no proper intermediate fields. So K is here, f is here, there is nothing in between other than K and f, of course. This is also very simple because if K, f, L is in between, this we know is P, let's say this is A, this is B. We know P is equal to AB, right? So we know P is equal to AB, but P is prime. So A is equal to 1 or B equal to 1. Any prime number cannot factor non-trivially. So if A equal to 1, that means K is equal to L. If B equal to 1, that means L is equal to F. Okay, so that also finishes the solution of this problem. So if you have a prime degree extension, there are no proper intermediate fields. So let me do one more example in a similar flavor. Let K over F be a field extension. So the previous problem and this problem are characteristic independent. I am not assuming anything about what the prime field is. It works for any prime field. Let K over F be a field extension and let alpha in K be algebraic over F. If the degree of alpha over capital F is odd, then what we can say is that F alpha is equal to F alpha squared. This is also really a consequence of multiplicativity of degree, but in a slightly different way. So let's do this. So we have K, which is actually not relevant. We are really interested in F alpha squared, F alpha, F. So remember, alpha squared certainly contains F alpha, is contained in F alpha because alpha squared is here. Alpha squared is a polynomial in alpha with coefficients in F. Namely, it is 1 times alpha square. So it is there. So F alpha squared is a subfield. What do we know? We know that alpha is algebraic over F of odd degree. So F alpha colon F is odd, right? Because again, remember, degree of an algebraic extension generated by a single element alpha is equal to the degree of the element itself. So this is odd. On the other hand, I claim that the degree of extension F alpha over F alpha squared is less than or equal to 2. So of course, it's greater than or equal to 1. Any degree field extension will have positive degree. it cannot have degree less than 1, right? So it's either it's at least 1. I claim that it's at most 2 here. This is because alpha satisfies a degree 2 polynomial. So the reason is this. The reason for the upper bound is that alpha satisfies a degree 2 polynomial over f alpha squared, namely x squared minus alpha squared. This is a polynomial in over the ring, over the field f alpha squared, right? Because alpha squared is an element of f alpha squared. So this is a polynomial of degree 2 over this. So if you take f equal to this, what is f alpha? This is alpha squared minus alpha squared, which is 0. So alpha satisfies a degree 2 polynomial. Hence, the degree of alpha over f alpha square is 1 or 2. It may not be 2, right? Because maybe alpha itself is in f alpha squared. So it can be 1, but it cannot be more than 2 because it satisfies a degree 2 polynomial. But suppose it's 2. That means f alpha colon f alpha squared is 2. But this is not possible, right? Because then 2 divides the degree of f alpha over f, which is not possible because since f alpha colon f is odd. Hence, f alpha colon f alpha squared is 1. It is either 1 or 2. It cannot be 2. So it has to be 1. That means f alpha is equal to f alpha squared. Right? There is a small observation here, which is that if you have a field extension, this I have used multiple times. Let k over f be a field extension. That means k is a field containing another field f. Then k is equal to f if and only if k colon f is 1. The degree is 1. So f alpha colon f alpha squared is 1. That means f alpha is equal to f alpha squared. So what we have is that this is equal. So this is a nice convenient statement. Sometimes that's useful to you. If you have an algebraic element whose degree is whose degree is odd, then if you take this field generated by the square of it, it's the same field. Okay. So now let's continue with some more problems. So this is the 4th problem. So let's do 5th problem. So what I want to do now is let us take 3 fields. Let's say k containing L, containing F are algebra field extensions. So what we have is that k over L. So I'll write it here, k over L over F. Suppose that k over L and L over F are algebraic, show that k over F is algebraic. Okay. So what I am saying is that this is algebraic, show that this is algebraic. So the 2 intermediate extensions are algebraic, show that the bigger extension is algebraic. So this is also easy. This uses something that we have done in one of the previous videos. So we need to show that what is an algebraic extension? It is an extension where every element is algebraic. We need to show that every element of K is algebraic over F. So let us take an arbitrary element. So let alpha in K be an arbitrary element. We are going to show that it is algebraic over F. We will show that alpha is algebraic over F. That's what our goal is. We do know that alpha is algebraic over L, right? Because K is algebraic over L. That means every element of K is algebraic over L. So there exists a polynomial f in Lx such that f alpha is 0. So there is a polynomial with coefficients in L which has alpha as a root. So suppose we have f as x power n, an minus 1, x power n minus 1, a1x plus a0, and remember ai's are in L. Since ai's are in L, each ai is algebraic over capital F, because L is algebraic over capital F. That means every element of L is algebraic over capital F. Now let's consider the new field. Let's call it L prime to be F adjoined A1 or rather A0, A1, A2 up to An minus 1. I claim that this is algebraic over F. So what is L prime? L prime is F. This we have done actually in one of the previous videos. So L prime is F adjoined A0, An minus 1, but each of them is an algebraic element. So you can actually one by one attach these. Okay, so you have these. This is algebraic because A0 is algebraic over F. A0 being an element of L and L is an algebraic extension of F. A0 is algebraic over F. It is algebraic, hence it's finite. An algebraic extension generated by a single element is finite. Similarly, A1 is algebraic over F. Certainly A1 then is algebraic over FA0. So this is finite. Everything here is finite. So L prime over F is finite. But a finite extension is algebraic. Okay, so what I want to say is that it is finite. Now, so let's keep that aside. What we have is K. Actually, what we have is K, L prime, and F. L prime contains L. So the full picture is like this: K, L prime over F. Remember, L prime is only L prime doesn't include all elements of L. It only includes these coefficients of this particular small f. What we have shown is that this is finite. Now I claim that alpha is algebraic over L prime. Alpha is algebraic over L, that we know, but it's in fact algebraic over L prime because the polynomial that alpha satisfies in fact leaves over alpha L prime, right? Because L prime was constructed so that this f that we have here, whose coefficients are a priori in L, are in fact over L prime, because A0, A1, A2, An minus 1 are all in L prime. So it is algebraic over L prime, and hence L prime alpha over L is a finite extension. So I will write it like this: L prime alpha over L prime is finite. So what I have is L prime alpha is finite, because again it's a finite, it's an algebraic extension generated by a single element, so its degree is the degree of alpha itself, so it's finite. So now this is finite, this is finite, hence L prime alpha over F itself is finite, because L prime alpha over F is L prime F dot L prime alpha over L prime. So this times this is L prime alpha over F. So if L prime alpha over F is finite, that means alpha is algebraic over F, right? Because the field generated by and L prime alpha is actually nothing but yeah, so it is a finite extension, so it is algebraic over F. So that means what we have shown is that it is contained in a finite extension. That means it is algebraic. And remember, alpha was an arbitrary element, and we have shown that it is algebraic over F. So K is algebraic over F. Okay, so that finishes the solution of that problem. What we have shown is that if you have two field extensions, intermediate ones are intermediate ones are algebraic, the bigger one is algebraic. Of course, if the whole thing is algebraic, it is a trivial fact that both intermediate things are also algebraic. So if you have K containing L containing F and K over F is algebraic, this is very easy. K over L is algebraic and L over F is algebraic. Because every element of K satisfies a polynomial relation over capital F, so it certainly satisfies a polynomial relation over capital L. Similarly, every element of L is an element of K. It satisfies a polynomial relation over F. So this is also algebraic. So this is easy. The converse is what the problem asks you to do. So, but altogether you can now remember this as saying, if you have three fields and they form a tower, the full thing is algebraic if and only if both the intermediate things are algebraic. So far we have done some of the problems. So I'm going to stop this video here. In the next video, we'll continue and discuss some more problems. Thank you.